into the very fabric of reality, the fundamental building blocks that make up, well, everything we see and touch. Our focus for this deep dive, a class of particles with truly unique properties.
Fermions.
Exactly. We're going to explore what makes these particles so essential, how their specific kind of quantum behaviors dictate the structure of the universe around us.
Right.
And why understanding them gives us a key to unlocking some of nature's deepest secrets.
In our guide, our source material here is Fermions, matter's quantum foundation. Think of this as your express route to grasping some seriously mind-bending physics.
Yeah, without getting bogged down in all the math straight away.
Exactly. Our mission today is to pull out the most crucial insights about fermions and their profound impact on the stability and organization of matter.
And do it in a way that's clear, hopefully engaging.
Yeah, definitely. Have you ever wondered, why atoms have that incredibly consistent structure? Or what force prevents colossal stars from just imploding under their own immense gravity? Well, the answer, or a huge part of it anyway, lies with these fascinating particles we call fermions.
Okay, let's unpack this then. The quantum world, it sorts its particles into two main categories, right? Fermions and bosons. What's the most fundamental difference?
The core difference lies in a fundamental quantum property. It's known as spin, which is a kind of intrinsic angular momentum.
Intrinsic angular momentum.
Right.
Yeah.
And fermions are defined by having half-integer spin values. So that's spin 1/2, 3/2, 5/2, and so on. Now, this might sound a bit abstract.
A little, yeah.
But this half-integer spin, it's the key characteristic. It makes them the fundamental constituents of matter as we know it, the stuff you can touch.
Half-integer spin, got it.
Yeah.
So if these are the building blocks of everything tangible, what are some of the most basic examples, the elementary ones?
Yeah, so at the elementary level, meaning they aren't made of smaller bits, we have particles like electrons, the workhorses of chemistry, electrical currents, and quarks. They come in 6 different types of flavors: up, down, charm, strange, top, and bottom.
Okay.
Then we have the leptons. That group includes the electron itself, plus its heavier cousins, the muon and the tau.
Right.
And their corresponding kind of ghostly partners, the neutrinos. Electron neutrino, muon neutrino, and tau neutrino.
Okay, so those are the fundamental indivisible ones. But you also mentioned composite fermions earlier. What makes something a composite fermion?
Precisely. Composite fermions are particles that are built from an odd number of these elementary fermions.
An odd number, okay.
Yeah. The classic examples are protons and neutrons found in the nuclei of atoms. A proton, for instance, is typically made of 3 quarks, 2 up quarks, and 1 down quark. A neutron is similar, usually 1 up and 2 down quarks. Because they're built from 3 spin 1/2 fermions, protons and neutrons themselves behave as fermions.
Ah, okay. The odd number 3 makes the whole thing act like a fermion.
Exactly. And what's also quite interesting is that even entire atoms or atomic nuclei can act as fermions if they contain an odd total count of these fundamental fermionic constituents, protons, neutrons, electrons, all counted up.
Really? Like which ones?
Well, helium-3 is a perfect example. It has 2 protons, 1 neutron, 2 electrons. That's 5 fermions in total, an odd number. So the helium-3 atom acts as a fermion.
Interesting. So it's the odd number of these fundamental building blocks that determines whether something composite behaves as a fermion. You mentioned spin earlier.
Right.
This isn't like a tiny spinning top, right?
Exactly right. That's a common misconception. This intrinsic angular momentum, or spin, it's a purely quantum mechanical property.
Okay.
It's not about physical rotation in the way we think about it in our everyday world. It's just an inherent characteristic, like mass or electric charge is inherent.
Gotcha.
And for all fermions, the spin value is always a half-integer multiple of a fundamental unit. For most of the elementary ones we've discussed, electrons, quarks, leptons, the spin value is specifically 1/2.
Spin 1/2.
Yep. And this seemingly tiny detail has absolutely enormous consequences for how they behave.
Okay, here's where it gets really interesting, I think. This brings us to the Pauli exclusion principle. Sounds like a very exclusive club. What's the core idea?
Yeah, it is exclusive. The Pauli exclusion principle, formulated by Wolfgang Pauli, it states that no 2 identical fermions can occupy the exact same quantum state at the exact same time.
Identical fermions,
Oh, yeah.
2 electrons.
Exactly. Think of a quantum state as being defined by a unique set of quantum numbers. These describe a particle's energy level, its orbital angular momentum, which is sort of related to the shape of its probability cloud, and its spin projection, which you can loosely think of as spin up or spin down.
Okay.
So if you have two identical fermions, say two electrons, they simply cannot have all of these defining quantum numbers be the same simultaneously. At least one number must be different.
Okay, so it's like each identical fermion needs its own unique quantum parking space, you could say. No two can park in the exact same spot.
That's a great analogy, yeah.
What are the ripple effects of this rule? It sounds pretty fundamental.
Oh, the consequences are truly profound. Let's think about atomic structure first.
Yeah.
Electrons orbiting an atom are fermions, right?
Okay.
So because of the exclusion principle, they can't all just pile into the lowest possible energy level.
Makes sense.
Instead, they're forced to fill the available energy orbitals in a specific, orderly way. Each orbital can hold a maximum of 2 electrons, and those two must have opposite spin projections, one up, one down.
Ah, okay.
This structured filling of energy levels is what gives atoms their shell structure, and that shell structure is the absolute foundation of the periodic table of elements and how different elements form chemical bonds.
Wow.
So the way these tiny electrons are forced to arrange themselves actually dictates whether an element is reactive or inert, how it bonds. It's like the fermion rule shapes the personality of each element.
So the very reason we have, chemistry, the incredible diversity of elements and molecules, it all boiled down to this quantum rule for fermions.
Yeah.
That's mind-blowing.
It really is. Without the Pauli exclusion principle, all electrons would collapse into the lowest energy state. You wouldn't have complex chemistry. Life itself would be impossible.
Just incredible. What other major implications does it have beyond atoms?
Another absolutely crucial consequence is the stability of macroscopic matter, especially very dense matter.
Okay.
The exclusion principle creates something we call degeneracy pressure. It acts as a kind of effective repulsive force between fermions.
A repulsive force.
Yeah.
But not like magnets pushing apart.
No, exactly. It's not a force in the classical sense like electromagnetism or gravity where particles interact directly through fields. It's more of a quantum mechanical resistance to being squeezed into the same quantum state.
Okay.
In incredibly dense environments, like in stars at the end of their lives, this degeneracy pressure becomes incredibly important. It counteracts the immense inward pull of gravity.
Ah. So that's the answer to my earlier question about stars collapsing.
That's a huge part of it. For example, in white dwarf stars, the revenants of stars like our sun, it's the electron degeneracy pressure. The electrons resist being forced into the same quantum states, and that pressure holds the star up against further gravitational collapse.
Wow.
And in even denser objects, neutron stars, it's the neutron degeneracy pressure doing the same job. Neutrons are fermions too, remember?
Right, because they're made of 3 quarks.
Exactly. So think of it like trying to cram too many identical marbles into the same tiny box. Eventually they push back, not because they're physically bumping in the usual sense, but because there's no more available space, no more available quantum states. That quantum pushback is what holds up these dead stars.
So these incredibly tiny particles are literally holding up the remnants of giant stars. That's an almost unbelievable thought. What about, ordinary matter here on Earth? Does this principle play a role in the materials around us?
Absolutely. Think about metals. The electrons inside a metal behave kind of like a sea. We call it a Fermi sea.
Fermi sea.
Yeah. The electrons occupy a range of energy states up to a certain maximum energy level, which we call the Fermi energy. The Pauli exclusion principle dictates exactly how these electrons fill up those energy states.
Okay.
And understanding this Fermi sea model governed by the exclusion principle is absolutely crucial for explaining why metals are such good conductors of electricity and heat, among other properties.
It's also interconnected, isn't it? From the smallest atoms to the largest stars, the fundamental behavior of these fermions is absolutely key.
Yeah.
Now, the outline also mentions something called Fermi-Dirac statistics. What is that all about?
Right. Fermi-Dirac statistics is basically the branch of statistical mechanics that gives us the mathematical tools to describe large systems containing many identical fermions.
Okay, so it deals with huge numbers of them.
Exactly. It was developed independently by Enrico Fermi and Paul Dirac, and it flows directly from the Pauli exclusion principle. It essentially tells us the probability of finding a fermion in a particular energy state within a system, usually at a given temperature.
So it's a way to statistically understand how these vast numbers of fermions behave collectively, given that they hate sharing the same quantum state.
Precisely. The core idea is captured in the Fermi-Dirac distribution function. While the equation itself can look a bit intimidating, it basically tells us the average number of fermions you'll find occupying a specific energy level. One key feature is what happens at absolute zero temperature.
Okay.
At absolute zero, all the energy states up to a certain level, that's the Fermi energy we mentioned, are completely filled with fermions, one fermion per available state, essentially. And all the states above the Fermi energy are completely empty.
Like filling a container up to a specific water line.
That's a good way to think about it. And the surface of that filled region, in energy terms, is what we call the Fermi surface. It's a boundary in energy space.
Okay, that makes sense. And what happens when things warm up, when we increase the temperature?
Right, so when you raise the temperature above absolute zero, some fermions gain enough thermal energy to jump up to energy states above the Fermi energy. They get excited.
Exactly. And that leaves some states below the Fermi energy unoccupied, like little holes.
Sure.
So the sharp boundary at the Fermi energy gets kind of smeared out. The transition from filled to empty states becomes smoother and more gradual as the temperature goes up.
Right.
But importantly, the Fermi-Dirac statistics always inherently limit the number of fermions that can occupy any single quantum state to a maximum of one, which, of course, is just the Pauli exclusion principle showing up in the statistics.
So this statistical framework helps us predict and understand how fermions behave in various systems. Where do we see this in action? What's it used for?
Oh, everywhere where fermions are the dominant players. It's absolutely crucial for understanding electrons and all kinds of solids, metals, insulators, semiconductors. I mean, that's the foundation of modern electronics right there.
True.
It also helps us understand the properties of atomic nuclei because they contain protons and neutrons, both fermions.
Right. And as we already discussed, it's essential for describing the extreme conditions inside those incredibly dense astrophysical objects like white dwarfs and neutron stars.
Fascinating. Now, let's delve a bit more into the specific types of fermions. We mentioned elementary and composite ones. Let's explore the elementary ones in more detail first.
Okay. Elementary fermions, according to our current best theory, the standard model of particle physics, are the fundamental building blocks. They aren't made up of anything smaller as far as we know.
The real bedrock.
Pretty much. So we have the quarks, as we said, 6 flavors up, down, charm, strange, top, bottom. They also carry a property called color, which is related to the strong nuclear force, not visible color.
Okay.
They have these weird fractional electric charges, like plus 23 or negative 13. And you never find them alone. They're always confined inside composite particles called hadrons, like protons and neutrons.
Always stuck together.
Always stuck together. And all quarks are spin 1/2 fermions.
Okay. And then the other group was leptons.
Yes, the leptons. This includes the familiar electron and its heavier siblings, the muon and the tau. And then their corresponding neutrinos, the electron neutrino, muon neutrino, and tau neutrino.
Right, the ghost particles.
Hey, yeah, they are pretty elusive. The charged leptons, electron, muon, tau, they feel both the electromagnetic force and the weak nuclear force. But the neutrinos, being electrically neutral, only interact via the weak force and gravity, making them very hard to detect.
Uh-huh.
And a really big discovery was that neutrinos, contrary to what we thought for a long time, actually have tiny but definitely non-zero masses.
Right, I remember hearing about that.
And this leads to this fascinating phenomenon called neutrino oscillations, where one type or flavor of neutrino can spontaneously morph into another type as it travels.
Weird.
It is. And just like quarks, all leptons are spin 1/2 fermions.
Okay. Now, you also mentioned different mathematical descriptions, Dirac, Weyl, and Majorana fermions. Can you give us a quick sort of simpler rundown of what those mean?
Sure. It gets a bit into the weeds of theoretical physics, but basically, most of the familiar elementary fermions in the standard model, like the electron and quarks, are described as Dirac fermions.
Yeah.
Think of these as your standard particles that have distinct antiparticles. So the electron is a Dirac fermion. Its antiparticle is the positron, same mass, opposite charge. Simple enough.
Yeah.
While fermions are hypothetical particles, they'd be massless, spin 1/2, and possess a property called chirality, which is like a fundamental handedness. Think left-handed versus right-handed. We haven't definitively observed fundamental Weyl fermions yet, though some effects in materials can mimic them.
Okay. Hypothetical for now.
Right, and Majorana fermions are even more exotic. These are hypothetical particles that have the unique property of being their own antiparticles.
Whoa, how does that even work?
It's mind-bending. It means the particle and antiparticle are fundamentally the same entity. Neutrinos are actually considered prime candidates for being Majorana fermions. There are major experiments underway right now trying to figure out if they are Dirac or Majorana. It's a huge open question.
That's definitely right at the cutting edge. Now let's circle back quickly to composite fermions. We talked about protons and neutrons being made of 3 quarks. What else falls under this composite umbrella?
Well, protons and neutrons belong to a broader category called baryons. Baryons are defined basically as particles made up of 3 quarks.
3 quarks baryon. Got it.
Yep. And since they contain an odd number 3 of fermionic constituents, the quarks each spin 1/2, baryons themselves always behave as fermions. They can have different total spin values, like spin 1/2 for protons and neutrons, or sometimes spin 3/2 for other more exotic baryons, depending on how the quark spins line up.
Okay. And you also mentioned earlier that entire atoms or nuclei can be fermions.
Yes, exactly. The rule is quite straightforward, actually. If an atom or an atomic nucleus contains an odd total number of constituent fermions, so you add up all the protons, neutrons, and electrons inside it, if that total sum is an odd number, then the entire atom or nucleus will behave collectively as a fermion.
Like the helium-3 example.
Precisely. Helium-3, 2 protons, 1 neutron, 2 electrons. Total equals 5 fermions, odd number. So the helium-3 atom is a fermion. Contrast that with the much more common helium-4 atom.
Okay.
Helium-4 has 2 protons, 2 neutrons, 2 electrons, total equals 6. Fermions, even number. So helium-4 behaves as a boson.
Ah, and that makes a difference.
Oh, a huge difference, especially at very low temperatures. Fermionic helium-3 and bosonic helium-4 exhibit completely different quantum behaviors when they become superfluids, for instance.
Yeah.
It all comes down to that even versus odd count of internal fermions.
Wow. Okay, we've covered the different types of fermions, elementary and composite. Now, let's maybe step back and look at the bigger picture again. What is the real-world impact, the cosmological significance of these fundamental particles?
Right. Well, where do we even begin? As we've sort of touched on throughout, fermions are truly the architects of the material world around us.
Yeah.
They are the fundamental building blocks of all ordinary matter, everything you see, touch, interact with, the very stability of atoms, the incredible diversity of chemical elements that make up everything.
The periodic table again?
Exactly. And the existence of different states of matter, solids, liquids, gases. These are all direct consequences of how fermions behave, especially driven by that Pauli exclusion principle.
And thinking bigger out in the cosmos.
Absolutely. The life cycle of stars, how they evolve, and the formation of those incredibly dense compound objects, white dwarfs, neutron stars, are deeply, deeply tied to fermion properties.
The degeneracy pressure we talked about.
Exactly that. Electron and neutron degeneracy pressure are what stop gravity from winning entirely at the end of a star's life, stabilizing these remnants. There's even something called the Chandrasekhar limit.
I've heard of that.
Yeah, it defines the maximum mass a white dwarf can have before electron degeneracy pressure just isn't strong enough anymore, and it has to collapse further, maybe into a neutron star or even a black hole. That limit is a direct result of the physics of electrons as fermions.
So the same quantum rule governing electrons in an atom also sets the fate of massive stars. That's quite a connection.
It is. It shows the universality of these quantum principles.
So fermions are not only the building blocks, but also, in a very real way, the stabilizers of the universe at its largest scales.
Yeah.
What about here on Earth, in, like, materials science, technology?
Oh, absolutely central. In condensed matter physics, the study of solids and liquids, the collective behavior of electrons, which are fermions, remember, gives rise to pretty much everything interesting.
Like what?
Well, electrical conductivity in metals, obviously, insulating properties in other materials, the behavior of semiconductors, which are the heart of all our electronics, transistors, computers, smartphones.
Right, crucial.
And even more exotic things like superconductivity. Interestingly, in many types of superconductors, pairs of electrons called Cooper pairs manage to team up and effectively behave like bosons, which allows them to flow with zero resistance.
So they can kind of trick the system by pairing up.
In a manner of speaking, yes. It's a fascinating collective effect. Also, magnetism in materials, and even really strange states of matter like fractional quantum Hall effect liquids, where electrons seem to act as if they have fractional charge. It all stems from the underlying fermionic nature of electrons and their interactions.
It really is also deeply interconnected. From the tiniest atom to the largest star to the chips in our phones. What about the very, very early universe? Did fermions play a big part right after the Big Bang?
Indeed. In those incredibly hot, dense first few minutes, Fundamental fermions and how they interact were absolutely crucial for what we call Big Bang nucleosynthesis.
Making the first elements.
Exactly. The formation of the first light atomic nuclei, mostly hydrogen and helium, a little bit of lithium, the relative abundances of quarks and leptons and their interactions through the fundamental forces set the stage for everything that followed. And they also played a significant role later on, as the universe cooled, in the formation of the large-scale structures we see today, the cosmic web of galaxies and galaxy clusters. Gravity pulled matter together, but the nature of that matter, being made of fermions, influenced how it clumped.
This has been an incredible journey through the world of fermions. But, like any great scientific exploration, there are always frontiers, unanswered questions driving research. What are some of the big mysteries still surrounding these particles?
Oh, there are definitely some big ones. One major area is still neutrinos. We know they have mass now, which was a huge discovery, but we don't know the exact ordering of their mass states. Like, which of the three types is the lightest, which is the heaviest? It's called the mass hierarchy problem. And tied into that is the fundamental question we mentioned. Are neutrinos Dirac fermions with distinct antiparticles? Or are they Majorana fermions, their own antiparticles? Figuring that out would be revolutionary. It could tell us about processes beyond the standard model, maybe even related to why there's more matter than antimatter in the universe.
Wow, okay, so understanding neutrinos could unlock some really fundamental cosmic questions.
Potentially, yes. Does the fact that they are so incredibly light compared to other leptons, like the electron, give us any clues about maybe their Majorana nature? Or are those perhaps entirely separate mysteries we just don't know yet?
And what about the huge differences in mass between all the different elementary fermions? The electron is tiny, the top quark is enormous.
That's another profound puzzle. It's often called the fermion mass hierarchy problem. Why is there such a vast range of masses among these supposedly fundamental particles? The electron is super light, the top quark is heavier than a whole gold atom. The standard model puts the masses in by hand using parameters called Yukawa couplings, but it doesn't explain why those couplings, and thus the masses, have the values they do. Why this huge spread? We have no good answer within the standard model itself. It points towards deeper physics we haven't uncovered yet.
So, needing physics beyond the standard model, are there theories that predict maybe new kinds of fermions we haven't found yet?
Absolutely. Many theories that try to extend the standard model do predict new fermions. A very popular one is supersymmetry, or SUSY.
Okay.
Supersymmetry basically proposes that every known particle has a superpartner particle with different spin properties. So every known fermion, like electrons, quarks, would have a bosonic superpartner, electrons, quarks, and every known boson would have a fermionic superpartner. These fermionic partners, like photinos or Higgsinos, would be new types of fermions.
So doubling the particle zoo, basically.
Pretty much, although we haven't found any evidence for these superpartners yet, despite extensive searches at places like the Large Hadron Collider. Another possibility is sterile neutrinos, hypothetical neutrinos, that would interact even more weakly than the ones we know, possibly only through gravity. Searching for these new predicted particles, fermionic or otherwise, is a huge driver of experimental particle physics.
This has truly been a deep dive into the quantum foundation of matter. Let's try to maybe summarize some of the absolute key insights we've pulled out.
Yeah, okay. So, in essence, fermions are these fundamental particles defined by their half-integer spin. Sounds simple, but
it leads to everything.
Pretty much. That spin property leads directly to the really crucial Pauli exclusion principle. No two identical fermions in the same quantum state.
Right. The no sharing rule.
Exactly. And that principle, along with the Fermi-Dirac statistics that describe large groups of them, is absolutely essential. It dictates atomic structure, chemistry, the stability of stars against gravity via degeneracy pressure, and all sorts of properties of the materials around us: conductivity, insulation, magnetism.
It's been quite a journey, hasn't it? Tracing the impact of these incredibly tiny particles from, inside the atom all the way out to neutron stars and the early universe. Hopefully, you, our listener, have had some genuine aha moments connecting these quantum ideas to the world you actually see and experience.
Yeah, hopefully. And as we wrap up this deep dive, maybe something to ponder. Given just how absolutely fundamental fermions and their rules are to the reality we perceive, what other apparently stable, predictable aspects of our universe might have even deeper, stranger quantum underpinnings that we just haven't figured out yet?
Ooh, good question. Or maybe just the fact that something as weird and non-intuitive as quantum spin ends up dictating the entire structure of matter. That's already pretty mind-boggling. What other quantum properties might be having huge macroscopic effects that we're only just starting to glimpse?
Indeed. The questions definitely keep coming. The exploration continues.
Well, thank you for joining us on this deep dive into the quantum foundation of matter. Until our next exploration, keep those questions coming and stay curious.